Okay, so actually I said last video was the last video, but this is actually the real last video. It's the hidden bonus last video. So we're going to do a couple of problems on this, like three of them, I think, and just to kind of give you a heads up for how to approach these Newton's first, second, and third law types of problems, these dynamics problems. These are what we call like an application of Newton's second law, where we're actually applying Newton's second law to a physical situation, and so these get kind of complicated. But if we take it really step by step and we're careful about everything that we do, it'll come out just fine. Maybe it won't make a lot of sense until we get to the end, but I think once you see it a couple of times, you'll probably get a feel for how to do these problems. So here's our first example. We have a block that's sliding on a rough surface because a spring is exerting a force on the block. Using the information provided, so the example, this information right here, using this information that is put in a box, try to find the block's acceleration. And so I said in one of the previous videos that the best thing that you can do to start off a problem that you're not sure how to approach is to draw a picture. So let's go ahead and do that as well. Here's our surface and the wall that the spring is attached to. This has friction, so I have these little lines here that show us that there's friction involved. Those little hash marks or whatever you want to call them, they say that that's a rough surface. Anytime that you see the words rough surface, just think friction isn't going to happen. So we've compressed the spring a little bit, and the total compression distance is 10 centimeters. So here's our spring compressed, here's our mass m, and maybe we could draw some other things if we wanted. Here's a velocity vector, at least the velocity we'd expect would be in that direction. We'd expect it to accelerate in this direction. We could probably put some force vectors on there, maybe like a friction this way, a spring force this way, overall leading us to that acceleration vector that points to the right. And also we need to define a coordinate system. So we'll say positive x is to the left, or sorry, to the right, and positive y will be to the up. So we know that this spring is going to exert a force, and we know that it's compressed. So our natural length would be something like this, L sub 0, or natural length of our spring. And that means that it's going to exert a force in the positive x direction. So that's what we've drawn for our spring force in red, in the positive x direction. Friction force always opposes the motion. And so if our motion is going to be to the right, our friction force must by necessity be to the left. We can set up, we could probably draw like a free body diagram if we wanted. So here's our mass compressed to a single dot. Here's a normal force, N vector. Down, we'll have our force of gravity acting. We'll have a spring force acting in this direction, F spring vector. And in the opposite direction, we'll have a shorter vector, F sub k. Again, this is going to be an unbalanced force type of problem. And so our spring force is going to be much longer than our kinetic friction force will. And that will end up causing a net force to the right, which will mean we'll accelerate to the right as well. All right, now that we have our visualization part out of the way, let's get down to some math. I'd say the first thing to do is to look at the x and the y direction of things. So here we'll do a column for x direction in blue, and then in red, we will do our y direction column. I'm going to go ahead and start out in the y direction. The reason why isn't important. You can start off in either direction, but I think if you start off in the y direction, oftentimes you'll figure out what your normal force is, and then you won't have to do it later. So starting off in our y direction, we'll apply Newton's second law, which says that our net force, F net, is equal to mass times acceleration in the y direction. And we'll make those vectors, and so we have F net sub y vector is equal to mass times acceleration in the y direction vector. We know that this is going to be equal to 0 because it's on a horizontal surface and we don't expect it to accelerate up or down. And so what we'll have is our net force is equal to, in the y direction, F net y is equal to 0. But our net force is the sum, the vector sum of the normal force, normal vector, plus the force of gravity vector. And so our normal force points up, so it's positive. Our gravity force points down, so it's negative. We get this relationship, normal force minus Fg is equal to 0. And then that gives us normal force is equal to the force of gravity but the force of gravity's equation is mg. So normal force is now just mg. And this isn't necessary to do every time. If you know that you're on a horizontal surface, you can probably just go ahead and say that n is equal to mg. But if you're not on a horizontal surface, or if you have another mass on top of your mass, you have to take those into consideration. So that's our important takeaway from this y component stuff, is that our normal force is equal to mg. And we're going to need that because we have a friction force. In general, if you don't have a friction force, you're probably not going to need anything going on in the y direction. Unless there's motion in the y direction. So if you are on a frictionless horizontal surface, you don't really need to worry so much about the y component stuff. You could if you wanted to. It's good form too. It's good practice too. You absolutely should, but it's not 100% necessary to solve a frictionless surface type of problem. But since we have friction here, we will need to solve n is equal to mg. So n is equal to mg, that's what we get from y direction. In the x direction, we can do something similar. We'll say our f net sub x is equal to mass times acceleration in the x direction, and those are vectors. So our f net is the vector sum between our spring force vector, f spring, plus our kinetic friction vector, and that's still equal to m times a sub x vector. We have an equation for spring, but let's and the friction force, both of them. But first, let's go ahead and go from the vector notation world into our scalar notation world. Our spring vector points to the right, and that's positive, so we'll call it positive f spring. And then our friction vector points to the negative direction, and so we'll call that minus fk, or plus a negative fk. And that will be equal to ma sub x. Again, you don't need to worry about pulling out a negative sign from your acceleration vector. If you think it's going to be pointing in the opposite direction, just leave it the way it is. Go through the process. At the end, it'll kick out a negative or a positive acceleration. That will give you the direction that you need. Okay, so spring force, we know that that is equal to minus k times delta x, and we know our friction force is negative fk, and we can substitute in that our friction force is negative mu k times our normal force, and that will give us m times a sub x. So that's all I have room for on this page. We'll have to go to the next page, so I'll just kind of zoom out, show you the whole setup for the first part, and then I will go ahead and swipe over to the next page and we'll do some copying of things. Here we are back. We have the old equation says minus k times delta x minus mu k times n is equal to m times a sub x. This all came from our free body diagrams and our careful analysis situation and application of Newton's second law, where this is our net force on the left, and on the right is our mass times acceleration for Newton's second law. So we know what k is, we know what delta x is, we know what mu is, we know what m and g are, and so we just need to solve this for our a sub x. But let's take a moment to kind of talk about some negative signs here. You might think that because I have a minus k delta x, I will be adding this negative up, and our acceleration will be bigger than it should be, and also pointed in the negative direction. But that's not what's going to happen, because delta x is also negative 10 centimeters, or negative 0.1 meters. And so that negative inside the delta x hidden in here will cancel out this negative on my minus k delta x equation, and that will give us a positive spring force. Hopefully that spring force will be bigger than our friction force, and if that's the case, we will have an acceleration to the positive, in the positive x direction. So if I plug in some values, I get minus k, which we said was 20 newtons per meter, times delta x, which is negative 0.1 meters, and then we have minus mu k, which is 0.35. Again, no units, no positives, no negatives on our mu k. It's a scalar, so it's just 0.35 and no units. So minus mu k times normal force, which we're going to say is mass, 300 grams, or 0.300 kilograms. So mu k times m times our gravitational acceleration, 10 meters per second squared. One more time, this is a positive 10 meters per second squared because we're not in the vector world anymore. We're in the scalar world. And so g is a scalar. It doesn't have a negative sign. It's always going to be positive here. If I called this mu k times n vector and said this was now mu k times m times g vector, that would be a whole different situation. And we'd be still adding these things together, and you should see it come out in the wash. But overall, our m and g, that comes from our normal force n. And so if I do this, I plug it all into a calculator, what I get is something around 0.95 newtons. If I look at my first term, I have this friction, or sorry, not friction, but a spring term. And so that has newtons per meter from K times meters. Our meters will cancel, leaving us with just newtons. Over here on the other side of things, this side of things, I have a kilograms, a mass. So mass times a acceleration, which is meters per second squared. And we said that is what a newton is. And indeed, we get a newton out. So when we add two things that are both newtons, we get a result that is in newtons. And this is 0.95 newtons. And that will be equal to our mass times our acceleration in the x direction. Notice how it's positive, and mass is always going to be positive. And so that means our acceleration will be positive, pointed in the positive x direction. That's what we're looking for. Our mass is 0.3, but if I divide both sides of this equation by mass, I will get then 0.95 newtons divided by 0.300 kilograms, and that will be equal to my acceleration in the x direction. And if I plug that into a calculator, I should get somewhere around 3.2 meters per second squared. And that will be my acceleration. In the x direction, at least. It's 0 in the y direction. So just to do one more thing and point a couple things, little intricacies out. Our acceleration vector in the x direction, ax vector, is equal to 3.2 meters per second squared. That's our magnitude. And its direction is in the positive x direction. Our acceleration in the y direction, a sub y vector, is equal to 0 meters per second squared, and that is in the positive y direction. It could also be the negative y direction, but it's negative 0 is still 0, right? So we just might as well call it positive. Then these are two different vectors, right? One of them is pointed entirely in the x direction, one of them is pointing entirely in the y direction. And if I add those two vectors together, like a tip to tail type of thing, I will get my overall acceleration, and that would be a, without a subscript, just a. So a vector is equal to ax vector plus ay vector, which I can write as 3.2 meters per second squared in the x hat direction plus 0 meters per second squared in the y hat direction. That would be my full answer for the full vector of acceleration, but a sub x would also be an acceptable answer if I were to ask you this type of question. However, if this were the AP exam, they would be very specific that they want the total acceleration vector. What is the magnitude of the acceleration vector? Not the magnitude of the x acceleration, but the total acceleration vector. And you'll have to use a Pythagorean theorem or whatever to find that. So that's one problem. And this is a pretty common problem where we'll have a spring and some friction, or two of these forces acting together. Well, we have like a friction and gravity, or a friction and a normal force, or a friction and a spring force, or a spring force and gravity, or all kinds of these ways that we could combine these things together to make a bunch of different real world scenarios. And then we'll have to apply Newton's second and Newton's first law to them and figure out some answers about it. Okay, so for the next example, I have some information on the left. Mass is 500 grams. That is equal to 0.500 kilograms. We have mu k value of 0.2, an angle of 30 degrees, a v initial of 0 meters per second, and a delta x of 1 meter. And the prompt is you place a block at the top of an inclined plane and let it slide. Our incline angle is 30 degrees. And you let it slide for 1 meter down the incline to the bottom. What is the final velocity of the block when it reaches the bottom? And this is not 1 meter vertically, this is 1 meter diagonally. So the total distance that we're going to slide down this is 1 meter, and that will be our the distance down the incline. So just to kind of like give us a real good physical view of what's going on. Here's our inclined plane. Here's our angle theta. We'll put our block up here with a mass m, and it's going to slide down this inclined plane until it reaches the bottom. And we should know that gravity is going to be the thing to drive it down this inclined plane. For sure, friction is going to have some effect, but it's not going to overcome gravity. And so if it moves, our gravity force in the parallel to our inclined plane will be greater than our friction force, and so it will cause that acceleration to change our velocity. Our initial velocity will start off at 0, and we will go to some final, and we'll have to figure out what that is. You can assume that this will be a constant acceleration type of picture. Usually these force problems are. So we can kind of start making sense of things. So let's say that this is my initial starting position. I'll call it x initial, and I'll say that is 0 meters. And then I'll go down here to the bottom, draw another line. That is my x final, which is 1.0 meters. And that's the 1 meter down the incline that we need. So when it says it slides down the incline, they mean this is a distance or a displacement that is parallel to this inclined plane and not like a horizontal or a vertical distance. I've talked about this before in class, and one of the things we like to do with inclined planes is rotate our coordinate system so that our x direction points parallel to the incline and our y direction points perpendicular or normal, normal force, normal to the incline or 90 degrees. So y direction is now pointed off of this surface, and x direction is parallel to the surface, which will make our lives a lot easier. And I will kind of point out why, even though I've done it in the past. I just want you to understand that it may look like it makes things really hard, and it kind of does at first, but ultimately it will save you a lot of time and a headache if you do it this way. So let's look at our y direction stuff, right? Actually, no, let's not do that. Let's draw a free body diagram first. So here's my free body diagram's dot. Here's my force of gravity. Force of gravity always acts directly down towards the center of the Earth. But our normal force always acts perpendicular to the surface. So it's going to be pointed off in this direction. My normal force. And my friction force will always act parallel to the surface. So there's my friction force F sub k. And now the only direction, or the only force vector you can see that's clearly in this parallel, this new x direction, is this friction force point in the negative x direction. And you'd say, well, that's not right, because if that were the case, you know, my intuition tells me, and Newton's second and first laws state that this will be accelerating up the incline because friction is pushing it that way. Why would it slide down the incline? And the answer is pretty simple. Now, this is our free body diagram. I'm going to put it in a box. I'm going to label it FBD. We don't draw vector decomposition inside our free body diagrams. Not in AP Physics. That's against the AP laws. So what we do instead is we'll draw it somewhere else. Here's our force of gravity pointed directly down. But if I think about it, my y direction is this way, and my x direction is this way. And let me change the color of that gravity vector so it's more clear what is a coordinate system and what is a vector. So vectors, we'll do those in red, and we'll do our coordinate system in black. So I know that my part of this is going to be in the y direction. Part of my force of gravity will be this way. Call that FGY. And then part of it, in fact, let me go back a little bit. We'll do this in different colors. We'll do FGY in orange. And then in, say, pinkish color, we will do FGX. So there they are, FGX, FGY vectors drawn for you. Now, we made an argument about how this is a similar triangle thing. If you want to see how that similar triangle thing works out, I can for sure do it for you, but this is not the time or the place. So I'm just going to be short about it and say that this right here, through the law of similar triangles, that angle is also the angle theta, which is our angle of incline. Now, I remember, maybe you don't, but I do for sure, we have that SOA, SOA, CA, CAH, and TOA. T-O-A-H? T-O-A. T-O-A. Right, it says that sine is opposite over adjacent, cosine is adjacent over, I messed up. It should be so, S-O-H, ka, C-A-H, and toa. So sine opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. Why am I writing this here? Well, because we need to use it to figure out what is a cosine and what is a sine. If I look at my angle, the thing that is opposite, sine opposite of it, is my FGX. And so my FGX vector is actually going to be just FG times sine opposite, so sine of theta. Similarly, for my orange FGY vector, this is the adjacent leg of this triangle, and so my FGY is going to be FG times cosine theta, which is different from what we saw in our vector decomposition for velocities. When we were doing projectile motions, we said that the x component of our velocity was always v times cosine theta, and our y component was always v times sine theta. And that's because we always gave our angle with respect to the x-axis. And so when we do that and we decompose our vectors, sines go with the y's and cosines go with the x's. But here we're given this angle with respect to a y-axis, and so it flips things. What happens is I get my x stuff for forces on inclined planes ends up having a sine with it, and my y stuff ends up having a cosine instead of the opposite way. So what we're going to have, maybe I'll just kind of I'll start this off here. We'll start off with our x direction stuff, and we'll just make a Newton's second law statement for that, which says that our net force is equal to m times a sub x. These are vectors, a vector or a sub x vector and f vector. In the y direction, we will have a normal or a net force as well, f net y. And that will be equal to m a sub y. Again, those are vectors. Let me put an x on this f net over on the left. All right, so the f net x is going to be the vector sum of our two x direction stuff. And the f net y will be the vector sum of our two y direction stuff. If we look at our picture or our free body diagram, we might be able to see that our normal force is pointed in the positive y direction. So our normal force will be in the y direction. Oop, I want to do that in red. So I'll say normal force vector. And the other thing that's in my y direction is not fg, but fgy vector. And that will give me m a sub y vector. On the other side, the x direction side of things, we have for sure our friction force, our kinetic friction, f sub k vector, and we're going to add another vector to that, another force vector. And that is also going to be the force of gravity, but it's going to be this new x component of it. So we'll call it fgx. And that will be equal to m a sub x vector. So here's our setup. We kind of started off some stuff. We have to go to the next page because I'm out of room, but then we'll talk about where to go from there. So next page, make our columns again, x direction. And the equation we stopped with was that our friction force, f sub k vector, plus our gravity force in the x direction, fgx vector, is equal to ma x vector. And then we had a y direction stuff right here. And what we got from that was that our normal force vector, n vector, plus our gravity component in the y direction, fgy vector, is equal to ma sub y vector. Now we can pull out our direction stuff. And again, I'm just going to do this in the y direction first. Usually it's kind of a good thing to do y direction first because it really quickly gets you what that normal force is and you can toss it right into your friction equation. So we'll do a normal force, or I'm sorry, the y direction stuff first. Our normal force points in the positive y direction. So we'll give it a positive n. And our gravity force points in the negative y direction. So we'll call that negative fgy. And this will be equal to ma sub y. And these are now scalars because we pulled out the signs, the negative sign from gravity and the positive sign here on our normal force. Those have been pulled out. Those are our directional components. So now what's left over is these n without a bar over it, which is a scalar quantity, and it's positive. So I'll have normal force minus the force of gravity magnitudes will give me mass times acceleration in the y direction. We know that that's going to be 0. That's usually the case, and that tells me n minus fg or fgy is equal to 0, or n is equal to fgy magnitude. So magnitude of our normal force is equal to the y component of gravity in our new coordinate system. Fgy, we have an equation for, that's Fg times cosine theta. And we have an equation for Fg as well. And so ultimately we can write that the normal force is equal to m times g, that's my force of gravity, times cosine of theta. Again, theta is the angle of incline. So I have an expression for my normal force, which I will use for my friction force in the x direction. Okay, back to our x direction stuff. We have a vector fk. It's pointed in the negative x direction, so I'll give it a negative sign and pull out that directional quantity. And so we have negative f sub k plus fgx, which is pointed in the positive x direction, so we'll just call it fgx, and that will be equal to max. This is not going to be 0 because it's our x direction, and it starts from 0 velocity, it accelerates down the incline and reaches some final velocity when it hits the bottom. All right, the next thing that we need to do is figure out some numbers. To get the numbers, we're going to have to kind of be careful about some stuff. I see a friction force, and I have an equation for that. So to get the numbers for it, I will need to plug in my equation first. My friction force, as we know, is mu k times my normal force. And then I have positive fgx, which we said was fg times sine theta. That will still be equal to max, ma sub x, mass times the x acceleration. Then I can plug in for my normal force what I found down here in my y component stuff. So I get mu k times my normal force, which will be mu k times m times g times sine, or times cosine of theta, not sine. See, I'm so used to it, just like you guys are. You're going to make this mistake. I guarantee it. You're going to make this mistake at least once per day. Make sure that you check. It's going to be exactly the opposite of what you'd expect. So if you see your normal force with a sign, that's not right. It'll be normal force will give you FGY, or normal force is equal to FGY. FGY is FG times cosine of theta, not times sine of theta. So I get my minus mu k times m times g times cosine of theta, plus my force of gravity, which is mass times gravity, times sine of theta. And this is still equal to m times a sub x. You see some stuff in here that looks kind of like the same, and we can certainly factor out an m times a g from both terms. And what I'd be left with is, we'll put this one first because it's positive. So I get mg times sine theta minus mu k times cosine theta. This will happen a lot in these types of problems. If you see this thing pop up where you have a sine theta minus mu k cosine theta, that's a good sign. It means that you're on the right track in the vast majority of cases like this. Okay, so this thing here is equal to m times a sub x. But if I divide both sides by mass, my masses cancel on both sides and they go away. And then I get g times sine theta minus mu k times cosine theta is equal to my acceleration in the x direction. From here, it's just a matter of plugging in numbers. 10 meters per second squared. Again, positive 10 because that's a scalar g. There's not a vector bar over the top. So positive 10 meters per second squared times sine of theta, which was 30 degrees, minus mu k, which we said was 0.2, times cosine of 30 degrees. Sorry, it's getting kind of hard to read at the end, but that's life. All right, if I plug this stuff into my calculator, I should get that my acceleration about equal to 3.2 meters per second squared. So now we have an expression for acceleration, and you're thinking, okay, how does that help me find a velocity? Well, now we have to look at our previous unit number 1, where we talked about motion at constant acceleration. Again, we'll assume that this is a constant acceleration because it is due to gravity. Usually gravity gives us a constant acceleration of g. And so if we're on an inclined plane, we will get another constant acceleration. It won't be equal to g, but it will still be constant, and that's what's key. So with constant acceleration, we have options now. We have one option that says v final squared is equal to v initial squared plus 2 times a sub x times delta x. We know delta x, that's 10 meters, or sorry, 1 meter. We know a sub x now, that's 3.2 meters per second squared, and we know v initial is 0 because we start from rest. So what I get then is v final squared is equal to 2 times a sub x times delta x, and then v final is equal to plus or minus the square root of 2 times a sub x times delta x. Now, is it positive? Is it negative? The answer is it's positive, right? It's sliding downwards. It's we said that that was the positive direction, and so that is going to be our positive, or our velocity will be a positive value when we're done. If we defined up the incline to be our positive x, we would end up with the same analysis, except we now use the negative version instead of our positive version that we're about to use. So v final is equal to square root of 2 times our acceleration in the x direction, 3.2 meters per second squared, times our delta x, which was 0.1 meters, the compression distance of our force, of our spring force. Sorry, the compression distance of our spring, which causes our spring force. If I plug all those values into a calculator, I get around, I think it's about 2.5, yeah, 2.5 meters per second. And that would be my answer for velocity final. But just to be thorough, let's look at some dimensional analysis. I have square root, and inside that I have 2, which has no units. I have a acceleration of meters per second squared, 3.2 meters per second squared, and I multiply that by a distance of meters. Ultimately, I will get the square root of meters squared over second squared, which is just meters per second, units of velocity. That's awesome. We're good. The answer would be 2.5 meters per second, and that would be our final velocity. What did we do? We drew a picture. We drew a free body diagram. We applied Newton's second law, Newton's first law if we needed to, and then we split the x and the y directions up, and then we applied our Newton's laws. We applied it to each direction. We were able to solve for the normal force, calculated as mg cosine theta. We plugged that into our x component stuff, which gives us this expression that says g times sine theta minus mu k times cosine theta is equal to our acceleration. We then calculated our acceleration's value, 3.2 meters per second squared. And then we maybe thought we were done, but not quite. We still have one more thing to do, and this is the application part where we start to ask things about, the velocity and the final velocity or the initial velocity or the time that it took to do this or the distance that it traveled to do this. So the application part is then taking the acceleration that we found using Newton's second law in the x direction and Newton's first law in the y direction, taking that acceleration and then plugging it into a kinematic equation to get a statement about the final velocity. So that is our answer, 2.5 meters per second, and we will have one more example that will kind of build off of this one as well in just a second. Okay, so next part, and final example of the day. We have the same inclined plane as before, but at the bottom is a frictionless surface and a spring with K value 15 newtons per meter. When the block reaches the bottom of the inclined plane, it will compress the spring. How far will the spring compress? So just like before, let's draw a picture. Here's our inclined plane. Angle is 30 degrees. Put our mass at the top. It slides down until it reaches the bottom, right? So this is maybe a t. The initial is 0 seconds. And at the final point, when we're at the bottom, here's our theta, here's our block, is now up against a spring. So we'll call this T1. And the spring is not compressed at this point. So it's just now making contact with the spring, not compressed. Spring is not exerting any force. Then at some later time, call it maybe T final, we will have the block. Oop, that's kind of bad. We will have, let me redraw that. surface. There's our surface. There's friction all the way until the end. So let me do that end part in a different color. In the blue, there is no friction on our surface. And what we have is our mass down here. It's compressed the spring as far as it will go, and now our V final is 0 meters per second. So we have a spring that will cause this object, as it slides down and reaches at 2.5 meters per second final velocity, it will then hit the spring, and the spring force will exert the spring will exert a force that will cause an acceleration that will quickly bring that velocity from 2.5 meters per second to 0. So it will compress the spring fully. Once the spring is fully compressed, we will have 0 velocity, no motion, until the spring starts to expand, pushes the block back up, and it slides up. So here are 3 situations. We should kind of realize that what's going to happen is we'll need to take the stuff we knew from before and go to our after situation. So just like in the previous problems, we should probably split things up into our X and our Y component. I'll do that on the next page. So we'll do blue for our X direction stuff and red for our Y direction stuff. We could go through and do the summing of forces and all that crap again. I'm not going to make you do that. We'll just go back to our previous discussion because it's the same situation. We just added a spring to the end now. So we should know that our normal force is going to be equal to mg times cosine theta. That's what we get from our Y direction. From our X direction, we should know that minus friction force plus force of gravity in the X direction is equal to ma sub x. And then what we have is at the end of the whole thing, we no longer have our gravity force and our friction force just acting. What we have now is a spring force. And so we'll say we're at 0 height. And that means that our gravity is not going to really affect much at that 0 height once we hit the spring, but some other things will come into play. So at the end, and again, this is our beginning. At the end of the motion, what we'll have is a mass times an acceleration, which is at 3.2 meters per second in the positive x direction. And that's going to be equal to our new F net. We'll call it F net x number 2. So our net force in the x direction at the bottom, when the spring is fully compressed, is going to be our spring force, F spring, vector, plus our friction force, Fk vector. Then I can pull up my directional stuff. My spring is going to be pointed up the incline, so that will be a negative direction. I'll get negative F spring, and I will have a negative Fk. But my friction force is going to now be pointed in the opposite direction, and it's going to be pointed down the incline. The force of the spring will be working against friction. We know the spring force is going to be up the incline in the negative direction, and so our friction force must now be in the opposite direction, positive. And that'll be equal to ma sub x. So I get my spring force, which is k times delta x. We add to that our friction force, which is mu k times n, and that should give us m times a sub x. We have negative k delta x, and remember delta x is negative, and so that will give us a positive pointing spring force. And so that might cause us some issues, but if we look at our friction force, it should give us a positive force thing as well. And so ultimately, if I think about my spring compression distance, it might be a negative value, but the direction that is compressing is in the positive direction. And so delta x is going to be a positive number, even though it's being compressed. So I will have a negative k delta x plus a mu k times n value. So mu k is mu k, but n, we know from our previous example, is mg times cosine of theta. So now I have this expression for our net force minus k delta x plus mu k times mg cosine theta. I don't have to decompose my kx, my spring force, because my spring force will be pointed entirely in the negative x direction, and so I don't need to worry about any of that stuff. I know what k delta x is, or k and delta x are, or no, sorry, I want to solve for delta x ultimately. So what I'm going to do is I'm going to add kx to both sides, or k delta x to both sides, and I will get that mu k times m times g times cosine of theta, the angle of incline theta, is equal to m times a sub x plus k times delta x. Then, and let me just draw an arrow to bring it up to the top, then if I subtract m times a sub x from both sides, what I get is mu k times m times g times cosine. See, I told you I'm going to make that mistake. So don't feel bad about making that mistake over and over again. If you do make it on like a test or something, I'm going to not take off a whole lot of points for that. Mu k times m times g times cosine theta, and we are then subtracting m times a sub x from that, and we will get a value of k times delta x. So from here, it's just divide through both sides by k, and my k's cancel on my right side. That leaves me with a delta x is equal to, now notice how, I'll circle these in, let's say green. I have an m divided by a k in both terms, right? M divided by k. So I'm going to factor out m over k just because I can. And what I'm left with on that first term is a mu k times g times cosine theta. And from the second term, it'll just be minus a sub x. Now I can plug in some values. My mass again is 0.500 kilograms. K was 20, I believe. Let's see, 15 newtons per meter. I'm multiplying that by mu k, which is 0. Where did I have mu k at? 0.2 times g, which is 10 meters per second squared, times cosine of my 30-degree angle. I'm running out of room here, so let me try to move some stuff a little bit. Oop, that's not what I want to do. Move some stuff a little bit over, a little bit further. Over that. Okay, so now I have that first part, the mu k g cosine theta, and then from that we will subtract our 3.2 meters per second squared from a, or a sub x. And then if I plug this stuff in, I should get somewhere around negative 0.06 meters is my delta x. And so our compression distance, the distance that will travel or it will compress our spring, is 0.06 meters. You could also call that 6 centimeters. You could call it 60 millimeters. You could call it 60,000 micrometers. You could call it maybe, I don't know, 0.00006 kilometers, whatever. I think these two are probably where we should stop, just because I don't want you guys giving me things in terms of like nanometers or something when it's like the scale of the average human experience on the meters, 10 meters scale. But yeah, either one of these is correct. However, the most correct ones are 6 centimeters, 0.06 meters, maybe 60 millimeters, somewhere around there, right? Something small, fewest number of digits is best. So that's our answer. That's how far we'll compress that spring. Tons and tons of work to get involved in it. But if you're very careful about it and you take things piece by piece and you draw pictures and you make sure your pictures and your math agree with each other, that is like the direction of your forces, if it should be in the negative direction, it's pointed in the negative direction, has a negative sign, all that stuff matches, it'll be okay. It just takes some work, it takes some time, so don't freak out too much about it. It is hard, it is physics, but it does work and it'll work for you eventually. So let me know if you have any questions about this stuff, if you need help on the worksheet that I handed out or I had Ms. Velchek hand out. I will get back to you with answers as soon as I possibly can. But until then, we will see you later and have a good day.